Anna and I are in the process of making things. Here she goes. We're doing this outside because it's about to get messy. Anna, would you like to explain what these are?
Questionable gelatin molds.
You look disgusting. So ready for this?
I don't even know if it's gonna come out properly.
Let's see.
Nope.
It's going. Look, the top's jiggling.
It's slippery.
Oh, there it goes. No?
Oh!
Oh, the pyramid collapsed.
Dang it.
That's so nasty. Ew! Next one. Anna is currently working on a chocolate and pure gelatin pyramid.
It's a great food pyramid right there.
That's right. This is a great food pyramid. Look at your little jello pyramid.
Oops, I forgot.
Mmm, delicious.
Look at that jello. Looks really cool in the case.
It does. I like the colors of that one the best.
Yeah. It's the Sith Wayfinder colors.
It really looks like the size of one too. Maybe you should spatula it.
Spatula.
Oh look, here comes Mom with her flowers.
Oh no, look like it's coming out of the side.
Whoa, there it
Oh,
goes.
look at your pyramid.
Ew.
Oh.
Nasty. Oh no, you lost the tip.
Did I?
Maybe?
Maybe.
Gentle.
I think I did.
Next time, I think put Vaseline inside.
I put olive oil. Do we have that?
I think the green is out, Chunk. I think the red might be a goner. Molted pyramid.
What's the tip?
Yeah.
So picture before.
Industrial design students. This is what they do in college. Here's the aftermath. That's right, students. Today's lesson is going to be all about food pyramids. Let's take everything we learned about those food chains and those food webs and use them to construct one final visual representation of energy. A food pyramid. Students, so I thought we would start by literally building a food pyramid. In a food pyramid, you always start with your producers, or your plants and bacteria that do photosynthesis, on the bottom. It's your first level. These plants support our next level, which are going to be our primary consumers. You know, things that tend to survive on just plants or chemosynthetic bacteria. In this case, I have birds. It's my second level. These primary consumers then tend to support our our secondary consumers, the carnivores. In this case, I have a very fierce and very hungry dog. And he'll provide what we'll call our last level in this sample pyramid. Own sample food pyramid here. That way we can add in some labels and gather our knowledge. Let's give this pyramid 4 different trophic levels. Or let's make it 5. Now remember from autotroph and heterotroph that troph is going to mean nutrition. So the trophic level is basically just going to be a hierarchical level. There's an order to it. And it's going to be determined by the animal's eating patterns. Basically, who does it consume and who's it consumed by. And all organisms on one trophic level are going to kind of have the same feeding patterns, either being herbivores, carnivores, primary consumers, etc. example, at the very bottom of the pyramid, supporting everybody with their beautiful photosynthetic powers, are the producers. These would include, yes, plants, but also some photosynthetic bacteria and some photosynthetic protista, who can convert the energy from sunlight into glucose that everyone else can consume. Since they can make their own food, producers are also known as our autotrophs. Remember, auto meaning self, and troph, nutrition. They're self-feeding. Who eats the producers? Well, the primary consumers. Since they can't feed themselves, they're considered heterotrophs. They eat others, specifically the producers. The way we're setting this up, it looks like the producers are supporting the primary consumers. These guys would be all of your herbivores. Having fun here. I don't think there's an ecosystem where rabbits and monkeys coexist, but you get the idea. All of these different things, including amoebas, would eat our producers. Primary consumers support our secondary consumers. Secondary consumers, of course, also have to be considered heterotrophs because they're eating other organisms. I can fill in my pyramid as I see tertiary consumers are supported by the secondary consumers, and quaternary consumers are supported by the tertiary ones. Now, I am no artist, and it definitely shows here. There are a couple kingdoms that we have left off, most noticeably the fungi and the eubacteria. That's because these are decomposers, and decomposers act at all different trophic levels. They don't depend on just one. It is actually not ideal for showing decomposers because if I put them at the top, that's not really true. Decomposers are some of the most plentiful organisms around. So let's just put them off to the side and show how each trophic level contributes to decomposers after they die off. Decomposers are then going to take all of that dead nutrient and they're going to recycle it back into a very valuable compound, nitrogen. Nitrogen is much needed by plants as fertilizers, and so it becomes a nice, beautiful, continuous cycle, a nice energy balance. Why do we do pyramids when we've already got wonderful food webs to depict what's going on? One thing is the shape of the pyramid. You might notice that we have a ton of producers, a few less primary consumers, and finally not that many secondary consumers. The reason for this is that there's a given amount of energy produced by each organism at each level. Say, for example, I make 10,000 kilojoules at the producer level. Only about a tenth of that, or 1,000 kilojoules, is then going to go on to the next primary consumer level. And likewise, out of the 10,000 kilojoules of energy at the primary consumer level, I'm only going to get a tenth of that, or about 100 kilojoules, up to this poor secondary consumer at the top. So basically, as you go from level to level, you're losing 90% of your energy at each level. So the shape of the pyramid actually mimics what happens within ecosystems, which is that you will always have a ton of producers, a few less primary consumers, and even fewer predators as you get towards the top of those food chains. And shape also shows us well that one ecosystem can only support one or two quaternary consumers compared to a whole host of producers. The reason behind this is something called the 10% rule, where out of all the energy at one trophic level, only 10% of it will be transferred to the next trophic level. Where does all that energy go? Well, you might realize as you're exercising and need more energy, you start breathing really hard. That's your body going through the process of cellular respiration, taking that glucose and making it into ATP, or energy that you can actually need. Now, this process is not super efficient. So that means that a lot of the energy stored in the glucose is actually going to leave your body as heat and other waste products. When your body has finally finished going through that process of cellular respiration and giving you the ATP you need, you're going to have lost 90% of the potential energy you could have had, and you'll only have 10% of the original energy left over to actually use. But as we consume organisms, our bodies work extremely hard through metabolism to convert that into energy we can use. We're going to give off a lot of that energy as heat, and we're going to lose a lot of it just in the process of metabolism. Now, to talk about energy, I'm going to talk about a unit called the joule. It's named after a French scientist who discovered it. And if I'm talking about 1,000 joules, that's going to be equal to what I call a kilojoule. And I'm going to abbreviate that as kJ. Out of all of my total producers, I've got 50,000 kilojoules of energy. Only 10% or 5,000 of that is going to be transferred up to the next trophic level of the primary consumers. The rest of it is going to be released as heat and metabolism. Likewise, out of the primary consumers' 5,000 kilojoules, only about 500 kilojoules will be transferred up to the secondary consumers. And so on and so forth, with only 10% of the total energy at each trophic level being transferred up to the next level through consumption. So that means going from having such a wide amount of energy available to only a tiny percentage of that available at the top, you can only support a few high quaternary consumer organisms. That means that 90% is going to be lost as heat and metabolism. If you're mathematically challenged, one way to do 10% of each of these numbers is simply to drop a 0 from the end. That will give you 10% at the next level. Drop a 0 from 5,000, I get 500. Drop a 0 from 500, I get 50. Drop a 0 from 50, and I'll get 5. The last reason why a pyramid is a great way to depict energy transfers in the ecosystem is that concept of stability. If you were to start to disrupt one layer, the whole thing could go crashing down. And this is where biodiversity comes into play again, because if you've got many more species in a pyramid, it's going to tend to be a little bit more stable. And if I lose one, or maybe and losing a couple species along the way won't be as hazardous for the whole ecosystem. That's all for today, students. You should have updated page 117 in your notes for energy or trophic pyramids. You should be able to now complete part 2 of your practice on Google Classroom, which does involve you making and designing your very own pyramid. And you know what? What the heck? Make a Jello pyramid while you're at it. Be an industrial design student and a bio one. See you next time.